Welcome everybody to lesson 12 of our friendly introduction to abstract algebra. We are in chapter 6, homomorphisms, and now it's high time that we take a digression and talk about maps. I could have or should have done that earlier in this course, but I did not want to intimidate the beginners, because some of those concepts, if you are new to this stuff, can be a little bit, well, intimidating or too abstract. So after some weeks have passed and you have gotten a little used to working with more abstract concepts, I think now is the right time to do this. And if you already know about this stuff, then you can completely skip this week or actually the next 2 weeks, because the problem set for this stuff here is quite long and elaborate, so I'm going to spread it out over 2 weeks. Okay, here's the definition. A and B are supposed to be sets, non-empty sets, so simply collections of objects, numbers, group elements, whatever. We're not going into axiomatic set theory here. And now a map from set A to set B is the following. Just for the terminology, sometimes I will call it a function. This is what you're used from high school. If the set A is a subset of the real numbers, and maybe also if B is a subset of the real numbers, then we will talk about a function, but map is more general. As we will see shortly, a map can be between any sets. They do not have to contain numbers, so most of the time I'm going to talk about maps. So our map is denoted with lowercase f. It goes from A to B. An element x of A is mapped to an element of B that we call f of x. Now notice the difference between those arrows. This arrow here is between the sets, and this arrow with this little line here means that one element of this set is mapped to an element of the other set. And now it is very important that a map is such a rule that assigns, first of all, to every element of A an so-called image f of x, and that this image must be unique. So every x in A is assigned to a unique element in B that we call f of x or sometimes y. And this is the image of x under f. Now some more terminology. A, where the x's live that I plug into f, is called the domain of f. Sometimes, at least in the German literature, A is denoted by d sub f, meaning the definition domain. But I don't think it's used that much in the American or English literature. We could call this here all the elements x that f can digest, or that I can feed into my map f. B, the so-called codomain of f, is simply where all the f of x live, that f puts out. So I plug in an x, and f is like a machine that spits out this image here, called f of x, and this here lies in the set B, which is the codomain. Now very important, this set here, f of A, notice the difference. Here we have an element, here I have the whole set. So this means something different than this here. This here is an element of B, whereas this here is a whole subset of B, consisting of all the images f of x, where x runs through the set A. Also in the German literature, this is often abbreviated by im for image, even in German, im f. And I haven't seen this as well that much in the English literature, so maybe f of A is a better symbol for the so-called image of f. Sometimes it is called the range of f, but I think this term is a bit older. In most modern textbooks, there is no mention of the range, but it is always called the image of f, and I'm going to stick to that. So to describe this in words, those are all the elements in B that are hit by f. So f spits out those images of those little x here, and all the elements of my codomain B that are hit by f are in the image of f. And very important, as I said before, f of A is not an element of B, but a subset of B, because it consists of all the images f of x. Okay, as I've said before, if you have already learned this stuff, this is all, of course, pretty trivial and tedious to listen to, but if this is new to you, I think it takes some time to digest. Actually, I teach this in my math honors course in high school. There are very, very bright children in there, but this subject is difficult for most of them. They have no problems with complex numbers, for example, but this here, the sets and the maps between sets, is still of another level of abstraction, I think. So I think it's good to take a closer look at a very simple example from everyday life, but in this notation here. So Anthony I call X, Barbara I call Y, and Charlie I call Z. Lowercase a stands for apples, lowercase b for bananas, C for cookies, and let's take donuts. That's a bit more interesting than dates, and then you have 2 healthy snacks and 2 not so healthy snacks. And now we look at different maps which simply assign to each of these persons their favorite food or their favorite snack or whatever you want to call it. So in yellow, F maps the set A, consisting of these 3 persons here, to set B, which contains these kinds of snacks. So for example, Anthony likes apples best, Barbara likes cookies best, and Charlie as well. Now, F is a map. This is the first point that can cause confusion, because up here we said every X in A must be assigned a unique element. Now you might argue, well, both here get assigned to the same element, namely cookies, but this is not a problem. The not uniqueness comes here in the next example. So in fact, I could have assigned to all 3 persons the same snack, like cookies. It would still be a map, because every person here is assigned one unique snack. It doesn't have to be a different snack for every person. So F is a map. It fulfills the requirements of being a map, and the image of F consists of apples and cookies, which is a subset of B and not the whole set B. So here, bananas and donuts are left out. Now our second map, F prime. This, of course, does not mean the derivative, but it's just a slightly changed version of F. Now here, for example, Anthony can't decide and says, well, my favorite snacks are bananas and apples. And Barbara says, well, I like donuts best, and Charlie now sticks with cookies. This is not a map, because now Anthony is not assigned to a unique snack, but to 2 snacks, apples and bananas. So this is not a map. I've called it G before, but we'll need that for the next example, because F prime of X, that looks too much. Okay, F prime of X simply looks like the derivative, so I'll call this map F tilde. F tilde of X is not unique. And Anthony couldn't decide if he likes apples or bananas best, so this is not a map. This is what would mathematically be called a relation. This is a broadened definition of a map, but we are not really going to need that. We talked about equivalence relations. There might be the right place to discuss relations in a broader sense, but we are not going to need that. So this here demonstrates this is a map and this is no map. Okay, now here are 2 more examples. G in green is almost the same as F, but now I changed the codomain. I'm allowed to do that. I can define here whatever I want to, so my codomain B prime now consists only of apples and cookies. And in this case, for example, Anthony still likes apples best, and both Barbara and Charlie decide they like cookies best. So this, again, is a map, no problem here. And the image of A now is complete B prime. This will lead to an important definition later. So you can always change the domain or the codomain. That's why it's very important to always give this information. You can't simply say, well, F is a map. You always have to specify what the domain and codomain are. Now H, again, here I take B double prime, consisting of 3 elements, apples, bananas, and donuts. And now this here clearly still is a map. Each element here is assigned to a unique element there. Again, the image of this map is the whole codomain. And one more thing, this here does not happen. There are no two elements that get mapped to the same. So this here is a one-to-one correspondence between A and B double prime. And this will be a very important map for us in the course of this course, for the rest of this course here. Okay, two more definitions. F is a map from A to B. Of course, always A and B are sets. M is a subset of A. This means it could be all of A. N is a subset of B. Here the same, it could be all of B. Now f of M is simply the collection of all the images f of x when x runs through the whole set M. This is called the image of M under F and is a subset of B. And of course, if I take M to be the complete set A, this is simply the image of F. Yeah, this is simply f of A from before. Maybe you can still see it here. So this is generalization of the image if I take subsets of A. Okay, the last new definition, but this is a very important one and possibly new to you. I take a subset of B, so I'm somewhere here in the codomain, B or B prime, doesn't matter. And now I pull this back to A, so this goes in the other direction. This here, f to the -1 of n, is called the preimage of n under f, or the inverse image. Now we have to be very cautious because we already know the concept of inverses in a group. And this suggests that f inverse is clearly the inverse of f, the inverse map. This is not true in general because a map F does not need to have an inverse. We're going to talk about that in some minutes. But this here does not mean F inverse in the group sense. Very important. So, and sometimes I've seen this notation, maybe this is a bit better here, these brackets, so that you do not confuse, because this looks exactly the same, like F is pushing M forward and F inverse is pulling in the same way the N backwards, but F inverse is not a map opposed to F in general. So, what does this set mean? It simply means I take all the elements of A such that their images f of x lie in N. So, for example, now we're going to look at examples shortly. So this clearly is a subset of A called the preimage of N under F, or also the inverse image. I think preimage is a bit less confusing. Now there's one very important special case. If N is a singleton map consisting of a single element, we leave these set brackets here away and simply write f inverse of y. Again, this might suggest that f inverse is a map because I apply it to an element. So again, please be cautious. This is simply a notation for this set here, which can be defined for any map, if it has an inverse as a map or not. Okay, very important point. So this is defined as this here, and this simply means all the x in A such that f of x lies in this set here. But what does it mean to lie in this singleton set? Well, the only possibility is that f of x is equal to y. So this here means all the elements of A that get mapped to this element of B called y. And this is called the fiber over y, of course under F, or the level set of y, of course again under F. Okay, let's take a look at our examples. First, the yellow example over there. If I take the set YZ, so Barbara and Charlie, and map it with F, I end up with a singleton set consisting only of cookies. Take a look at that. This is depicted here. Y and Z get both mapped to C, cookies, so this is the image of this set here. Now the preimage of the set bananas and donuts is empty. Why? Because there is no arrow ending at either banana or donut. So none of those elements get mapped to banana or donut in this example. So this might also happen that the preimage of a set is empty. And now the fiber of cookies no pun intended, the fiber of cookies under F consists of Y and Z, yeah, because of this here. Those are the only elements that get mapped to C. Now you might say, well, of course it does, because we have this here. This is not the same, because there could also be another person like David who also likes cookies, but I haven't put him in here. So this here does not necessarily imply this. Yeah, we're going to talk about the relationship between F and F inverse a lot more later, but here you really have to be careful. I think F inverse is really one of the most intricate or complicated notions when you first learn about this stuff here at a beginner's level. Okay, in the purple example, we had this special map that gives a one-to-one correspondence, and now it's not surprising that for each element here in our codomain B double prime, so apples, bananas and donuts, the fiber consists exactly of one element. It is neither empty nor contains more than one element, so the fiber of A under H is Anthony, X. The fiber of bananas under H is Charlie, and the fiber of donuts under H is Barbara. And as trivial as this all may seem, also these childish examples, I think they help a lot to really understand these new notions. And I cannot overstate the importance of these definitions here. So you should really invest some time the next 2 weeks in trying to do as much of the problems or exercises from problem set 12. We now come to a very elementary yet very, very important proposition when dealing with maps together with set operations. So the setting is always the same. Let F be a map between sets A and B. We take subsets of A, M1 and M2, subsets of B called N1 and N2, and then the following holds. First, if M1 is a subset of M2, then so are the images. F of M1 is then automatically a subset of F of M2. The same is true for taking the preimage. If N1 is a subset of N2, then the preimage of N1 is a subset of the preimage of N2. Now, what about the union of sets? Remember, the union of M1 with M2 is the set of all elements that lie in M1 or M2, not either or. That's important. So the union of these two sets is all of that, not excluded that here. It's possible that an element lies in M1 and M2, it can still lie in the union. So a non-exclusive OR on the level of elements, this is the union here. And then if I map the union with F, it's the same as mapping M1 and M2 separately and then taking the union in B. With intersections you have to be careful. The image of an intersection is only a subset of the intersection of the images. This set here might become smaller by mapping it. We will give an example, or you will. This is going to be an exercise. So here, careful when dealing with intersections of sets, but taking pre-images is unproblematic in both cases. If I take the pre-image of the union or the intersection, it behaves well. So in both instances here I have an equal sign. So this here can't happen with pre-images. It's very, very important that you do some of this stuff yourself. So for the proof, we're only going to take a look at this one here. The rest is left as a very important exercise if you're seeing this kind of stuff for the first time. If not, then it should be pretty trivial or obvious for you, but if you're a beginner, please take this seriously because you need this a lot of times when dealing with our homomorphisms. Okay, let's try to prove this here. Okay, we're going to prove this in two ways. First in the long way and then in a condensed way where we do two steps at one time. So, to prove the equality of two sets, because those are sets here, you can always show that this set here is a subset of this one, and then the other way around, that this set here is a subset of this, and then you have shown equality. So let's start with this inclusion here. So you take an element of this set. Remember, the preimage lies in A, so we call the elements here X. Now what does this mean? We simply have to apply the definition of the preimage. This means that f of x lies here. Now comes the definition of the union of sets. As explained before, this means that f of x lies in n1 or f of x lies in n2. It can also lie in both at the same time, but that's not important here. So this here I call I or 1, and this here I call double I. So what does this mean? If f of x lies in n1, then by definition x lies in the preimage of n1 under f, because this simply means that f of x lies in n1. Okay? But now, this here always lies in this set together with f inverse of n2, because if I take the union of two sets, then the set gets bigger or stays the same if this one lies inside of that one. It cannot become smaller because they'll take all the elements that lie here or here. So if you read this, this means that x lies in this set here, and this is what we wanted to show. We started with an x here, and we arrived at the conclusion that x also lies in this set. And of course, now let me be lazy, if f of x is an element of n2, then by definition x lies in f inverse of n2, and again, this is a subset or the same set as this union here. So again, x lies here, so this proves this inclusion. Okay, now for the other inclusion, we start with an element here, and we have to show that then it automatically lies in this set. Okay, now again, by definition of the union, this means that x lies here, or maybe both. Now, in case I, this means f of x is an element of n1. This is exactly the definition of the preimage, but same argument as above. n1 is always a subset of this union here, because this union gets bigger or stays the same, and this means that x is an element of the preimage of the union n1 with n2. Because f of x lies here, x lies there, so this is what we wanted to show. And of course, again, I'm being lazy, if this is the case, then f of x lies in n2, again n2 is a subset of this here, so x lies in this, and this is the proof. Okay, now here's another more elegant way to prove this, not showing two inclusions, but showing both inclusions at once by using equivalences. If this is suitable for you as a beginner, you have to decide for yourself. Maybe it's better to do it as demonstrated before. So, and it's in the end simply applying the definitions, nothing more, nothing less. We start with an element in this set, and we show that it lies in here if and only if it lies in here. And then of course the sets must be the same, because they have the same elements. So, if x lies here, by definition of the preimage, f of x lies in this set, here. Now comes the definition of union. If f of x lies in this union, it lies here or here, non-exclusive or. Then again comes the definition of the preimage. If f of x lies here, then x lies in f inverse of n1, and the same with n2. Now again comes the definition of union. X lies here or here if and only if it lies in the union. That's simply the definition of union of two sets. And that's it. This clearly is more elegant, but maybe too fast. Decide for yourself when you do the rest of the proof. Please do not neglect this exercise. If you're new to this, really try to get a good grasp of these elementary facts in dealing with maps and set operations. So this concludes this little part of the proof, and the rest is left as an exercise.